In this lesson, we're going to take a look at the Atwood's machine and kind of talk about what makes this particular device interesting when we start talking about the equilibrium or non-equilibrium or Newton's second law. So an Atwood's machine is a contraption of massive objects. Usually this contraption is connected by a string, a cable, or rope. It almost always involves a pulley of some kind. And the thing to point out is the acceleration of these objects depends on many different factors. The first of which being what are the masses of the objects. The second of which being how are the objects oriented with one another. The third, is there any friction acting on any of the objects? Is there any friction in the wheel? Those are all things that might change the acceleration. So the first Atwood's machine I want to look at is this one here, shown to the right, and has two objects connected by a string over a pulley, and the mass of object 1 as shown is 15 kilograms, the mass of object 2 is 5 kilograms. And I want to determine two things, the acceleration of the two masses and the tension in the string. Now you might say, oh well, that's easy, the tension in the string is mass times gravity, the weight of one of the blocks, but wait, which block? Is it the 15 kilogram block? Is it the 5 kilogram block? And if weight and tension are the same, how can that block accelerate? We can all agree that this system is going to accelerate. We can probably also agree that mass 1 is going to accelerate downward and mass 2 is going to accelerate upward because mass 1 is bigger in mass than mass 2 is. So those are things we know for sure are going to be true. Another thing that we can probably say is true is that the acceleration of these two masses is the same because they're stuck in the string. So what I'm going to do is I'm going to draw a free body diagram for each of the masses independently. And so on the left-hand mass, we have M1G and tension. On the right-hand mass, we have M2G and tension. I can say the net force acting on mass 1 is M1A, and the net force acting on mass 2 is M2A. And so I could say M1G minus T is M1A, because I'm pretty sure that M1 is going to accelerate downward, so I'm going to guess the weight of mass 1 is bigger than the tension in the string. And I'm going to say the tension in the string minus the weight in mass 2 is M2A, because I'm going to guess that M2 is actually going to accelerate in the upward direction, meaning the tension is bigger than the weight. Now, some things to point out about this system. First thing to point out is that the tension is going to be the same in both of these strings. That's really a Newton's third law argument. If the string is pulling on mass 1 is also pulling on the string in the same force, and that string has to be pulling on mass 2 in exactly the same way. So really what this string does is it's a way of connecting mass 1 and mass 2. So the tension acting on mass 1 is really the force mass 2 applies on mass 1. The tension acting on mass 2 is really the force mass 1 applies on mass 2. So I'm going to calculate the tension saying it's M2A plus M2G, and then I'm going to plug that all into the other equation. So I'm going to do substitution. The reason why I'm doing substitution is I know that the tension is the same in both these equations and the acceleration is the same in both these equations. So if I go and I factor in that negative sign, I get negative M2A minus M2G. I add the M2A over to the other side, and I have an equation where the only thing I don't know is A. So I can factor out the A by factoring out the sum of the masses, and what I get for this Atwood machine is M1 minus M2G divided by M1 plus M2. Let's take a step back and think about this. Does this make sense? What this is telling you is that the acceleration of the system is dependent upon how much bigger the larger mass is compared to the smaller mass and the total mass of the system itself. That it's going to get bigger if the difference between the masses is bigger, and it's going to get smaller the more massive the objects are to begin with. I think that both of those make logical sense. If we plug in our numbers, we get 4.9 meters per second squared as the acceleration. The next step I can do is to plug that A into my tension equation that I solved in the third line down on the right hand side. T equals M2A plus M2G, and just plug in A, G, and M2, and I get 73.5 newtons as the tension of the string. Why don't we rearrange the system a little bit? And in this system I have a cart that has a mass of 650 grams. It's connected by a string to a frictionless pulley and a hanging mass of 250 grams. And I want to determine what the acceleration of the cart is. I also want to answer the question, is the tension in the cable equal to the weight of M2? Is it greater than the weight of M2? Or is it less than the weight of M2? Maybe take a second and just make a guess of what you think it probably will be. So if we think about this system, what we know for sure is going to happen if I let go of M2, M2 is going to be pulled downward. It's going to pull the string and pull M1 toward the right. And M2 is probably going to accelerate downward, and M1 is going to accelerate to the right. So I know for sure that it's going to accelerate in that direction. The second question, is the tension equal to the weight of M2? Well, it can't be equal to the weight of M2 because if it was, M2 can't accelerate because sum of forces would be 0. If the tension is greater than the weight of M2, well, M2 would have to accelerate upward. So it must be less than the weight of M2 in order for M2 to accelerate downward. So let's draw our two free body diagrams. On my cart, I have the tension in the string pulling me to the right. I have weight and I have normal force. We know the weight and the normal force are the same. I don't know what the tension in the string is. For the hanging mass, I have tension in the string pointing upward and I have weight pointing downward. The only thing I know about the tension in the string is that it's got to be smaller than what the weight is. So for object 2, I'm going to say the sum of all my forces is M2A, and it's got to be the equal to the weight of M2, M2G, minus the tension. And so which forces do I want to include for the cart when I actually go to calculate this out? Well, there's really only one force in the direction the cart accelerates, and that's the tension. The cart is going to accelerate to the right. I'm going to guess the weight and the normal force of the cart are the same thing. So M1A is actually equal to T. Now, kind of like in the last one, I'm going to say that A for the cart and A for the hanging mass are the same thing. And I'm going to say these two tensions are probably the same too. And so I can substitute in M1A for tension, and guess what? We now have an equation we can solve for the acceleration. That M2A plus M1A equals M2G. I can factor out the A, divide by the sum of the masses, and there we go. The weight of cart 2, or weight of block 2, divided by the total mass. If you take a step back and ask yourself, does this make sense? What this is really saying is that the acceleration of the system gets bigger if the mass of M2 gets bigger, and it gets smaller if the total mass of the system gets bigger. Basically, if the cart gets bigger, the acceleration is going to get smaller, which both make sense. As kind of an aside, what if instead of separating this out into two separate objects, we thought of this as just a system of objects? The only force that's acting on the system that will accelerate the system is the weight of M2. The total mass of the system is M1 plus M2. So if we thought of it that way, I would say the net force acting in the system, M2 plus M1 times acceleration, is equal to the weight of M2. Well, there I can solve for the acceleration right away. So in this problem, thinking of the two objects as a system of objects might actually be a faster way to solve this problem, and is actually a shortcut to solve certain Atwood's machine problems. And this one, that works pretty well. So in the next lesson, we're going to start looking at gravity in a bit more detail and how we can begin to describe that force in another way.